Hello everyone, myself Dr. Ashish Arora, Assistant Professor in ABES Engineering College, Ghaziabad. Today our topic of discussion is Euler's Theorem for Homogeneous Functions. Outlines for today's topic are homogeneous function, Euler's Theorem for homogeneous function, deductions from Euler's Theorem, and question based on Euler's Theorem. Before studying Euler's Theorem, we'll know about homogeneous function. A function fxy is said to be homogeneous of degree or order n in the variable x and y if it can be expressed in the form x to the power n phi y over x or y to the power n phi x over y. An alternative test for a function fxy to be homogeneous of degree or order n is that f tx comma ty equal to t to the power n f x comma y. If we replace x by tx and y by ty, then we will get right-handed side as t to the power n fxy. Then we can say that our given function is homogeneous. Now we'll take an example to show that whether a given function is homogeneous or not and what is the degree of a homogeneous function. Suppose we are given a function fxy equal to x square plus y square equal to x square plus y square divided by x plus y. If we replace x by tx and y by ty, then we will get right hand side as t square x square plus t square y square divided by tx plus ty. Then take t square as common from numerator and t as common from denominator. Then we get right hand side as t into x square plus y square divided by x plus y. So f tx comma ty equal to t to the power 1 fx comma y. Now this is the definition of homogeneous function. If a function f is homogeneous, then f tx comma ty should be equal to t to the power n fx comma y. Here the value of this n is 1. So we can say the function fxy is homogeneous function of degree 1 in variables x and y. Similarly, in this example, we can show the degree of the given function is half. We'll apply the same formula, x replaced by tx, y by ty, and we will get right hand side as t x plus y divided by under root t under root x plus under root y equal to t to the power half into fx comma y. So we can say that fxy is a homogeneous function of degree half in the variable x and y. Now we'll discuss Euler theorem on homogeneous function. If u is a homogeneous function of degree n in x and y, then x into del u del x plus y into del u del y equal to nu. Here n is the degree of given homogeneous function and use that homogeneous function. It can be extended to a homogeneous function of any variables. Thus, if u is a homogeneous function of any number of variables, so thus if u is a homogeneous function of degree n in x and y, then x into del u del x plus y into del u del y plus z into del u del z equal to nu. This is the Euler theorem for 3 variables, and on last page we have discussed the Euler theorem for 2 variables. Again, if u is a homogeneous function of degree n in x and y, then x square del 2u del x2 plus 2xy del 2u del x del y plus y square del 2u del y2 equal to n into n minus 1 into u. Here u is a homogeneous function of degree n. Here are deductions from Euler's theorem. If fu equal to v x comma y, where v is a function in x and y of degree n, then x into del u del x plus y into del u del y equal to n into fu divided by f dash u. Second, x square del 2u del x2 plus 2xy del 2u del x del y plus y square del 2u del y2 equal to phi u into phi dash u minus 1. Here phi u equal to n into fu upon f dash u. Remember one thing here, fu is a homogeneous function of degree n, not u is a homogeneous function of degree n. In case of Euler theorem, we will take u is a homogeneous function of degree n, and in case of deduction from Euler's theorem, we will take fu as a homogeneous function of degree n in the variable x and y. Now we'll take a question in which we will verify Euler's theorem for the function u equal to sine inverse x by y plus tan inverse y by x. First, we'll check whether u is a homogeneous function or not. To check whether a function u is homogeneous or not, we'll replace x by tx and y by ty. Then we will get cancel t in numerator and denominator both. So we'll get sine inverse x by y plus tan inverse y by x. So utx comma ty equal to t to the power 0 into sine inverse x upon y plus tan inverse y by x. And we know that t to the power 0 equal to 1. So we can write 1 as t to the power 0. And by the definition of homogeneous function, utx comma ty should be equal utx comma ty should be equal to t to the power n ux comma y. So we can see that here the value of n equal to 0. So we can say u is a homogeneous function of degree 0 in x and y. So now we have proved that here u is a function of homogeneous function of degree 0. Now we can apply Euler's theorem because if a function is not homogeneous, then we cannot apply Euler's theorem. We know that by Euler's theorem, x del u del x plus y del u del y equal to n u. Number one, question number first. Here n is the degree of given homogeneous function, and we have already derived that degree of given homogeneous function is 0. So we can write x into del u del x plus y into del u del y equal to 0 into u equal to 0. So right hand side equal to 0. For the verification of Euler's theorem, we will show left hand side equal to right hand side, and the value of RHS equal to 0. Now we show that the value of left hand side is also 0. Now differentiate partially equation number 1 with respect to x. Sorry. Now differentiate partially, not equation number 1, given function u sine inverse x by y plus tan inverse y by x with respect to x. So what we'll get? Del u del x. Del u del x means the partial differentiation of u with respect to x, treating y as constant. So differentiate u with respect to x, then 1 upon under root 1 minus x square upon y square into 1 upon y plus 1 upon 1 plus y square by x square into minus y upon x square. Now we'll take LCM. Del u del x equal to y square minus x square into 1 by y plus x square by x square plus y square into minus y upon x square. Now multiply del u del x by x. So what we'll get? We can cancel y here and we can cancel x square here. So multiplying del u del x by x, we will get x by under root y square minus x square minus xy divided by x square plus y square. Now we will find the value of del u del y, which means partial differentiation of u with respect to y. So 1 upon under root 1 minus x square by y square into minus x square by y square plus 1 upon 1 plus y square by x square into 1 by x. Here we have differentiated u with respect to y partially. Now we'll take LCM. Y by under root y square minus x square into minus x by y square plus x square upon x square plus y square into 1 upon x. We can cancel y and x. So this is the value of del u del y. Now multiplying del u del y by y, what we get? Minus xy divided by under root y square minus x square plus xy divided by x square plus y square. We can say different. This is the question number A and this is question number B. Now adding A and B. Adding A and B, we get x del u del x plus y del u del y equal to x del u del x del u del x plus y del u del y equal to x divided by y square minus x square minus xy divided by x square plus y square minus x upon under root y square minus x square plus xy upon x square plus y square. So we can cancel these terms. We will get answer as 0. So x del u del x plus y del u del y equal to 0. This is the value of left hand side. So we can say here left hand side equal to right hand side. Hence Euler's theorem is verified because left hand side equal to right hand side and both sides are equal to 0. Hence we have verified the Euler's theorem. Now we'll take next question. Next question is question number 2. So next question is u equal to tan inverse x square plus y square by x minus y, and we have to show that number first x del u del x plus y del u del y equal to sine 2u, and second x square del 2u del x2 plus 2xy del 2u del x del y plus y square del 2u del y2 equal to sine 4u minus sine 2u. So first we'll check whether u is a homogeneous function or not. So we can say easily that here u is not a homogeneous function. So here we can check u is not a homogeneous function by applying alternative tests by replacing x by tx and y by ty. Now we'll check. Let tan u equal to x square plus, sorry, here x cube plus y cube. So here now tan u equal to x cube plus y cube divided by x plus y. So this is like function of x and y. Now we'll check whether fxy is homogeneous or not. For this we'll apply the same procedure. We will replace x by tx and y by ty, and we'll get t cube x cube plus t cube y cube upon tx plus ty. Take t square, so t cube is common from numerator and t is common from denominator, and we'll get t square x cube plus y cube divided by x plus y. So here we get f tx ty equal to t square x cube plus y cube divided by x plus y. So here we can say fxy equal to tan u is a homogeneous function of degree 2. Now by Euler's theorem, x into del f del x plus y into del f del y equal to nf. So here the value of f is tan u. So x into del x of tan u plus y del y of tan u equal to n. The value of n is 2 because the degree of the given homogeneous function is 2. 2 into tan u. Now differentiate tan u with respect to x and differentiate tan u with respect to y. Then x into the sec square u del u del x plus y into sec square u del u del y equal to 2 into tan u. Now we can take sec square as common. So x del u del x plus y del u del y equal to 2 tan u divided by sec square u, and we can write tan u as sin u upon cos u and sec square u as 1 by cos square u. So we'll get 2 sin u cos u. This is equal to sine of 2u. So this is our first part. Now we'll prove this part number 2. Similarly, we can prove part number 2 by applying deduction of Euler's theorem. For part number 2, Here phi u equal to sine 2u, which is equal to phi u, and phi dash u equal to 2 cos 2u. We know that the differentiation of sine 2u is 2 cos 2u. Now applying the deduction of Euler's theorem, what we'll get, x square del 2u del x2 plus 2xy del 2u del x del y plus y square del 2u del y2 equal to phi u into phi dash u minus 1. We have the value of phi u and phi dash u, so we can write it sine 2u 2 cos 2u minus 1, and we can write sine 2u into 2 cos 2u minus sine 2u, which is equal to sine of 4u into sine 2u. So this is the proof of part number second. So this is the answer of question number 2. Here are the references.